Introduce the speakers and can you people see my screen?
It's coming up.
So we have 6 short talks. So we'll start with the first 3 sets. The accelerating deep learning with hybrid parallelism and MVAPICH to GDR that will be presented by Arpan. He's a PhD student working in the MVAPICH team. His current research focus lies at the intersection of HPC libraries and deep learning frameworks. He's working on parallelism and distribution strategies for large-scale DNN training. He actively contributes to projects, the IDEAL project, MVAPICH to GDR software, and also the LBAN deep learning frameworks. The second presentation will be made by Quentin Anthony. He's also a PhD student and a member of the MVAPICH team involved in the deep learning side and as well as the MVAPICH to project and MVAPICH to GDR and IDEAL project. He will be talking about optimizing training of super resolution images on modern HPC clusters. And the third presentation will be done by Dr. Amir Sakhi. He's a research scientist in the team where he's involved both on the high performance big data project, also on the MVAPICH project. And his research interests include architecting robust libraries and tools for big data computation with emphasis on machine and deep learning. So he will talk about towards Java-based HPC using MVAPICH to library. So in yesterday's my roadmap talk, I presented some of these things at a very high level. Now we'll try to take a look at much more detail. So let's get started. I think Arpan.
Sure, Dr. Panda. Let me share my screen. Okay, I hope you can see my screen.
Yeah.
Okay, great. 1 second. So, hello everyone. Thank you, Dr. Panda, for the kind introduction. So today in this talk, I'm going to talk about accelerating the deep learning training with the hybrid parallelism and MVAPICH to GDR. So we are going to focus on the out-of-core models and some in-core models also, and how can we use the hybrid parallelism to accelerate the training and enable the training on out-of-core models. So a little bit of introduction. As we all know that deep learning is a subset of machine learning, and the main difference between the deep learning and machine learning is the way we extract the features. I'm not going to talk about it in detail because we already know all of these things. So let me jump directly to the distributed or parallel training strategies for deep neural networks. So broadly, these techniques can be divided into 3 categories. The first one is the data parallelism, and then we have layer and the domain parallelism. So data parallelism is one of the most common and the widest and widely used technique. So in this, we replicate the model on all the machines and then we distribute the data. However, in this presentation, we are going to focus more on the layer parallelism and the domain parallelism. So layer parallelism is used to train the out-of-core models, the models that cannot fit inside the memory of a single GPU or a CPU. So how can we train such models? The only way to train such model is to distribute the model across multiple machines. And the second technique is the domain parallelism. As the name suggests, it depends on the type of the layer. So for example, if you're using the convolution layer, then you can distribute the convolution layer in several different ways. Like you can distribute it spatially along X and Y direction, or you can use the channel parallelism and distribute the channels across multiple machines. So first, let's talk about why data parallelism is not enough. So as we all know that data parallel training has a major limitation. That is, it cannot train the model that cannot be fit inside one processing element. And this is very common. This is not like a anomaly, or it is not the thing that we don't see very often. So here I'm giving an example. So if you are training any model on the ImageNet challenge images, then yeah, you can train it using the data palette training. But if you want to increase the image size, like if you want to try 1K by 1K images or 2K by 2K images, then most of the models become the out of 4, meaning they cannot fit inside the inside one processing element. And these images are fairly common. Like if you take your iPhone or Android device and capture a picture with it, then the image will be easily like 2000 or 3000 pixels. So how can we train the state-of-the-art models on such large images? And the areas such as pathology has very large images, which makes the training impossible. So that is why we need a model parallelism and also the memory aware designs. So if you're just using the model parallelism and distributing the layer on multiple processes, then you will not get very good performance. For example, let's say your model fits on 4 GPUs. So even on the 4 GPUs, the maximum trainable batch size will be 1 because of the memory requirement. So how can we accelerate the training of such models and enable the training with the large batch sizes? So this is the problem we are trying to solve with our memory aware designs. And as you can see that, like in this figure, we are showing the memory utilization with respect to forward and backward pass, for forward and backward pass with respect to time for 2 iterations. And you can see that here we have both free memory and the compute available. So how can we use this memory and compute to accelerate the training? So this is the GEMS design we proposed in a supercomputing conference. So this paper was published in previous supercomputing conference. So we also call this as a bidirectional parallelism because first you start with the GPU 0, do the forward and backward pass. So once you finish the backward pass on the last GPU, then you can begin the forward pass from GPU 4. So that is why we call it the bidirectional parallelism. And in this way, we are using that free memory and compute. And since we are training 2 model replicas, so that is why we need all reduce operation to synchronize the training. And this is the kind of improvement you can expect. So here is the result of GEMS at the scale, and you can see that we are achieving 97.32 scaling efficiency on 1024 GPUs. It won't be possible without the optimized communication primitives from the MVAPICH to GDR library because of the increased communication requirement. For example, we are sending the weights, we are sending the activations and errors using the point-to-point operations in the model parallelism, and then we are doing one extra all reduce operation also. So that is why if we don't have these optimized communication primitives, then we won't be able to achieve this kind of scaling efficiency. So now now we show that how can we exploit the GEMS in the AI-driven digital pathology. So in the digital pathology, we have images like 100,000 by 100,000 pixels. Obviously, these images cannot fit inside a single GPU. We need to, in order to make the training possible, we need to use the tiling approach. But because of the memory limitation, the size of the tile is limited to just 256 images, 256 pixels, which because of that, we lose the structure information in the whole slide images. So can we use GEMS to train on the larger tiles like 1024 or 2048 pixels? So we used GEMS and we were able to reduce the training time from 32 hours to just 27 minutes. So now the next design is for the transformer models. So transformer models has gained a lot of traction in the community in the recent time, and they give a state-of-art accuracy for the natural language processing and speech processing problems. So we can use data parallelism for most of these models, but the problem is that the data parallelism does not use the inherent parallelism between the transformer models. So that is why we are going to use the domain parallelism to accelerate the training. So here is an example of multi-branch DNN architecture, and the transformer model is one of them. So we in this type of architecture, we have branching out, like the layer one is branching out into several layers, and then we combine the output into one layer. So this is the multi-head attention module in the transform model. So we can use the subgraph parallelism to accelerate the training. Like we can put the layer 2 and layer 3 on GPU 1, layer 4 and layer 5 on GPU 2. So in this way, we can execute these layers parallelly on multiple GPUs. The one problem with the subgraph parallelism is that we cannot use it for the common layers like layer 10 and layer 1. So that is why we combined our designs with the data parallelism and was able to achieve very good speed up with respect to data parallelism. Here you can see that we are achieving over 3.05x speed up over data parallelism. So, and we are always better than the data parallelism even on 1024 GPUs. So what is making this speed up possible? So normally I say this, it is the communication runtimes like MVAPICH to GDR, which makes the training possible, which advances the growth in the parallelization strategies and enables the training of state-of-the-art models. Without these optimized communication primitives, we cannot train such large models or such large state-of-the-art models. So with this, I conclude my talk. And so in this talk, we talked about the model parallelism and the domain parallelism and how can we achieve better scalability with these designs using the MVAPICH to GDR. Thank you. So I would be happy to take any question if there are any.
Yeah, Arpan, thanks. Are there any questions for Arpan? You can directly ask under Q&A or through Slack, or if you'd like to be unmuted and ask questions, that will also be fine. Okay, if not, let's move just to save time. We can always have the questions going behind the presentation. So Quentin, you can get started. You are muted, Quentin.
Okay, can you hear me now? Okay.
Yeah.
Okay. So as Dr. Pena mentioned, my name is Quentin Anthony. I work on the MVAPICH User Group. Today I'm going to be discussing about scaling single image super resolution training on modern HPC clusters and just some earlier experiences on this. I'll be referencing here this paper here, our SCADL paper, which you can see for more details on this. So first I'll go into some introduction on sort of what a deep learning framework is and what the state of deep learning is, and then we'll go into some background on super resolution. So we've discussed a lot about deep learning frameworks throughout this conference. They're just high-level APIs where you can easily implement and experiment with deep neural networks. Several have emerged, but PyTorch and TensorFlow have kind of emerged as the two dominating frameworks. We'll focus on PyTorch in this work, and then we'll also be focusing on NVIDIA GPUs for distributed training. So some background first on distributed DNN training. I'll go quickly through this. So deep neural network training consists of two phases. First, you go through the forward pass to the network and calculate the loss, and then you propagate that loss to the backward pass. And since this is really compute intensive and there's a lot of data you need to process, MPI-driven training is on the rise and distributed training at large is on the rise. So there are three primary approaches to distributed DNN training. The first and most popular is data parallelism, which is the focus of this paper. We duplicate the model on each GPU and then synchronize parameters after each training step with allreduce. And then there's model parallelism where you split the model, and hybrid parallelism, which is a mix of the two. So we'll be focusing on exclusively data parallelism for this paper. As a background on MVAPICH 2 and some GDR enhancements that we have for deep learning training is we have CUDA IPC designs, which is an interface for communicating across GPUs within a node. It's pretty old, since CUDA 4.1, and then many of the advanced collective and point-to-point designs in MVAPICH GDR use CUDA IPC and depend on it. So we need to ensure that CUDA IPC is being used for deep learning training if we want the best performance. And then a second enhancement that I want to discuss and we'll be exploring in the paper is the registration cache. So it enables a zero-copy transfer of large messages, which in large messages are most frequent in deep learning training, across InfiniBand without requiring memory registration on cache hits. So previous MVAPICH GDR versions disable the registration cache for deep learning workloads due to a conflict with TensorFlow's custom memory allocators, but this isn't the case with PyTorch, so we want to measure to see how much effect the registration cache has. So then what is super resolution and what is EDSR? So super resolution is any time that you're scaling up an image from some low resolution to a higher resolution. And it's learning, for deep neural networks, it's learning a mapping between these two. And so it's deep neural networks understand basic relationships of like what a window is, for example, then instead of something like a bicubic algorithm, we can learn to apply a window here as sort of a high level explanation of why deep neural networks are useful here. So we chose EDSR as a representative super resolution model due to its accuracy and its open source implementation in PyTorch. So then as more motivation is, we can see that for an example classification model like ResNet 50, we can get extremely high throughput at about 360 images per second, but for EDSR, it's much, much lower, usually about 10 images per second. So super resolution DNNs require a lot more computation per image since they're so much larger, and we can see that they could greatly benefit from applying HPC to them. So we built all of this work on top of Horovod, which is a distributed training framework that primarily uses data parallelism. It's a middleware between the DL framework and the communication backend, in this case MPI, and it's strongly dependent on Horovod Performance in MPI or Nickel or whatever backend you use. So we added Horovod support to EDSR. And further, we first compared the performance before and after without doing any sort of MVAPICH 2 level enhancements. So this is the default Horovod performance for EDSR. Training performance, we're seeing images per second, so throughput on the y-axis, and we can see only about a 55 to 65% scaling efficiency because these models are large and are stressing both Horovod and the communication backend. So we made some enhancements. We noticed that PyTorch recommends that the CUDA visible devices be set. So in essence, CUDA IPC was being disabled. Since CUDA IPC couldn't see local GPUs, it couldn't be applied. So MVAPICH 2 was being bottlenecked by CUDA IPC. So our primary enhancement here is we added an intermediate visible device list so that MVAPICH 2 can still see local GPUs, but PyTorch can't. And that ensures that we're still using IPC while also making sure PyTorch runs effectively. And a secondary enhancement is that we evaluated the effect of the registration cache on deep learning training performance. And these two together constitute the paper. So for performance evaluations, we ran on the Latency supercomputer, which has 4 V100 GPUs per node and 2 Power 9 CPUs. And then we used the latest at the time software libraries, MVAPICH GDR on Horovod and PyTorch. So now we have the scaling results. So these are the results of enabling IPC and registration cache. MPI is without both enhancements. MPI reg is with only the registration cache, and MPI opt is with both IPC and registration cache. And we can see that we get, with the registration cache, we get about 5% improvement, so moderate, and about a pretty good hit rate. And then with CUDA IPC, we can see about 26% improvement in training performance. And that's from Horovod being able to see local GPUs. And then we also profiled the Horovod performance, so we can see that all message sizes were performing better than both Nickel and the default MPI before these enhancements were made. And then we also saw significant improvements in scaling efficiency because the Horovod bottlenecks were being removed. And then finally, we have some more profiling results before and after. So the MPI would be the default MPI before creating these optimizations, and then MPI opt would be after with CUDA IPC and CUDA reg. And due to the large messages are due to the Horovod tensor fusion, where Horovod just batches or fuses together small tensors into a single large all-reduce operation. And then further, we see again the profiling results. We're seeing that latency is significantly improved for large messages, and this makes sense because CUDA IPC in particular is only enabled for large messages and is most impactful. So it's critical. One of the takeaways here is it's critical that users first profile their deep learning workloads before applying any MPI designs to make sure that these advanced designs that we have in MVAPICH GDR or Nickel or whatever else are being correctly applied. So we're seeing about a 45% improvement overall in total all reduce time after correctly applying the MVAPICH GDR designs. So in conclusion, image super resolution is growing in popularity. Deep learning super resolution models like EDSR require extremely long training times and a lot of computation. So and these novel DNNs bring about novel communication bottlenecks. So we recommend that detailed profiling of middleware is critical to identifying these bottlenecks and to ensure that your backend and every layer of the software stack is being applied correctly. And that in order to effectively scale to hundreds of thousands of GPUs, we need to ensure DL frameworks are using advanced MPI features properly. So thanks, that's all I have. If there are any questions, happy to answer them.
Thank you, Quentin. Are there any quick questions for Quentin? In the Q&A box or on the Slack, I don't see anything yet.
Okay.
So thanks then, Quentin. Let's move to the next talk. Amir, you can get started. Yeah.
Right. So thank you, Dr. Panda, for the introduction. Today, I'll be talking about some of the Java bindings work that we are working on in the MVAPICH 2 project. Here is the outline of my talk. So I will first introduce the problem and just some notes on design and implementation. Then I will present some early performance results, and I will conclude the talk with a summary. So there has been some on and off interest in producing Java-based Java bindings for MPI. So I think a couple of decades ago, there was a forum called Java Grande Forum, and this actually produced an API for Java called MPI Java 1.2. And then there was another API that followed, it was named after, it was called MPJ API, but it was just a minor upgrade. Some, naming conventions were changed. However, today there exists some MPI libraries, and some of the popular ones are MPI Java. There is a pure Java one called MPJ Express that I worked on earlier, and Fast MPJ. Open MPI, which is another production level MPI library, also has Java bindings. And one of the challenge here is that all these different MPI libraries, they have API mismatches. So if you have written an application with one of the libraries, it's not necessarily portable. So this is something that this Java-based HPC or Java-based MPI libraries, they need to fix, hopefully. Why Java? I will not say a lot about this in the interest of time, but our motivation here is that this is one of the largely adopted programming language by the big data community. And if we want to support any kind of communication in big data frameworks, like let's say Spark, for example, so we are going to require using MPI. So we are going to require some kind of Java bindings around MPI library. So essentially that forms the motivation of this work. So as I said, this effort aims to produce prototype Java bindings for the MVAPICH 2 library. And initially what we are planning for is to come up with a subset of MPI functions like blocking, non-blocking point-to-point functions, blocking collectives and strided blocking collectives, and also have Java bindings for communicator and group management functions. So the API that we chose to use is the same as what OpenMPI Java bindings is using. There is a slight modifications And as part of this work, we also have to produce a test suite to check correctness of Java bindings. So for the C-based MPI ecosystem, there exist a lot of mature benchmarks that can instantly be used to test functionality if MPI libraries are performing correctly or not. But that ecosystem does not exist for the Java world. So we need to work on that as well. And also in a parallel effort, we are also adding support for Java micro benchmarks in OMB suite. So initially, similar to what features work we are working on, we will produce OMB benchmarks for point-to-point blocking collectives and strided blocking collectives. And again, this is the architecture of MVAPICH 2 software family. So we really don't want to touch any communication related code, or we simply want to have a shim layer or a thin layer on top of the MPI that makes use of the existing protocols designs that are already available in the MVAPICH 2 library. So previously, I've actually worked on this library called MPJ Express. The approach that we used in that particular software was to implement the whole standard in the Java programming language. So in that, which is actually pretty complicated, you have to implement, support a new entire ecosystem and do that from grounds up. So the goal here in this case now is to keep the current Java layer bindings as minimal as possible. And this is also the approach taken by other MPI libraries like MPI Java and also OpenMPI. So what is the main challenge here? So I will just, there are a few challenges, but I will just focus on one challenge for today's talk. And it's essentially the data movement, let's say from the Java layer to the C layer. So for example, if I'm communicating, if I'm just using blocking send and receive, so at the sender end, I'm just doing mpi.com world send. So this data gets sent from the Java layer and this goes to the receiver and it's received by a blocking call to receive. And then S array here and R array here are essentially Java objects that are located on the Java heaps. And so this is where the challenge comes in. So this thing that I have in my figure, this is basically a Java garbage collector. So Java is an automatic, it provides you automatic memory management. So if you're allocating memories, you don't need to free them. The promise is that Java will take care of all the objects and everything, which basically means that this array that is used to communicate data, this can actually move throughout the memory. So the garbage collector that we have no control over and it runs non-deterministically, it can run anytime and decide to move the reference of this S array inside the heap anywhere. So when I'm communicating this data stored in S array using, let's say, from the native or C MPI send call, I need a pointer to this S array. So one of the biggest challenges of the first step here is that I need to get a pointer of this S array in the native C code, right? And if I make the problem essentially that we are tackling here is that if I do this thing, I need to make a copy of this in the C code, right? So if I'm communicating, this S array, I need to make a copy of this, and this leads to some performance degradations. So as part of step 2, I will simply communicate this data, but then this data copy again happens at step 3 at the receiver end. And again, let me emphasize this, and this happens because we are communicating data from Java arrays, and Java arrays can move inside the heap memory at any time because of garbage collection, and we have no control over it. So this is again emphasizing this particular point. So for example, here if you see, if we just focus on this first box, I'm trying to communicate data from this integer array, which is called array. I'm just sending, let's say, first 100 integers from this particular array. And then this is how my send method looks like. So because we are trying to keep this layer as minimal as possible, so inside the send method, we simply just have a call to a JNI function called native send. And this JNI is called, it's a layer called Java native interface. What this lets you do is it lets you call C functions from the Java code. And this is how my C code looks like. So this the box at the bottom here. So this is called a native send function, and this yellow thing is the buffer that is passed to me from the Java layer. And what I need to do here is that the JNI interface provides me functions like get int array elements, for example, and I will simply get a copy of this buffer that I'm trying to communicate as a buffer pointer. I will get a copy of this thing that I can then communicate using MPS send function. And at the end of the function, because I've initially made a copy of the buffer that I want to communicate, I need to release this particular copy. Because if I'm updating the copy that I made, I need to write back to the original array as well. This might not be important for the sender, but this is obviously important for receive, because the counterpart function of this native send is going to be native receive, and that actually receive contents from the receiver, and it needs to update the Java object as well. So as you can see here, because of the way things are designed, or because of the way how the Java language works, I have to make a copy of this particular thing, and this actually leads to some performance overheads when communicating Java arrays. So this is the approach that we have. This slide is overviewing the approach that we have taken. So our Java bindings are going to support communication from two main data structures. One is a Java arrays, and this is what traditionally has also been supported by existing MPL libraries. But obviously, as I discussed earlier, this leads to one extra data copy at the sender and the receiver. But there is another approach as well, and that another approach is pretty useful, and we are evaluating that, and which is to employ this so-called direct byte buffers. So what are direct byte buffers? So if you look at this particular picture, so we have the Java virtual machine, and then we have the Java code, Java garbage collector, memory that we are allocating. The Java virtual machine typically will be stored in the heap memory, and normally Java objects are indirect byte buffers. So they look like something like this, like an indirect byte buffer. They have no connection with the native memory, and the Java garbage collector can move them at any point in the memory. But then Java also has this new feature called direct byte buffer. Well, it's not new anymore. It's been there in the language for more than a decade now. But what this direct byte buffer does is that this is simply a pointer to some native memory, and this memory is like pinned. It will not. This is not subject to garbage collector. If you're allocating this kind of memory in your program, you are responsible for deallocating that as well. So we are also, we are relying on this direct byte buffers to somehow avoid that extra data copying that that essentially takes place when we are trying to communicate Java objects. So these are some preliminary latency comparison numbers. X-axis here is the message size going from 1 byte to 8 kilobytes. Y-axis is latency in microseconds. And we are comparing, MVAPICH 2 Java bindings for arrays and direct byte buffers with OpenMP Java bindings and their implementation of direct byte buffers. And as you can see, for the buffers interface, which are blue and red, we are observing similar performance. There is a little bit of overhead for our Java arrays implementation, and we are optimizing this particular aspect of the implementation. And these are preliminary bandwidth comparisons. So this overhead of data copying, this is obviously more visible for large messages. And this, if you compare this black line with this blue line, here, for this black line, we are communicating Java arrays. And for this blue line and the red line, we are communicating direct byte buffers. So we don't have numbers here for OpenMP Java arrays because we are using a benchmark OSU bandwidth, and that OSU bandwidth uses non-blocking point-to-point communication. And OpenMP Java bindings do not support communicating Java arrays using non-blocking point-to-point functions. And this is because, obviously, to avoid the overhead that's incurred. But if we try to calculate bandwidth for OpenMP Java bindings with different set of functions, or let's say with blocking send and receive, we observe similar performance for their interface as well. So obviously the overhead that I've just mentioned, that is there for Java arrays, that also exists in OpenMP implementations. So this leads us to think like, should we just, why not just use byte buffers in application? So why are we actually supporting communicating, data from Java arrays? Why not just, ask application developers to use byte arrays, byte buffers in their program, store data in byte buffers. So byte buffers have versions that allow storing, let's say, integers, longs, floats. So why not just ask people to use, or application developers to use these instead? But it's not that simple. So I will elaborate that in this particular picture. So while communicating data from Java arrays might be slower, but doing computation data with data stored in Java arrays is much faster than using byte buffers. So I will illustrate that with this picture and with the result here. And here what we have done is that we have simply added data validation as a dummy compute in the OSU latency test, right? So we are still doing OSU latency, but before I communicate the data, I obviously fill the send buffer with some data and we check that at the receiver end. So obviously once we are filling data at the sender end and checking the data at the receiver end, we are traversing Java arrays and the direct byte buffers. And as you can see here, this is actually only comparing MVAPICH2 numbers with Java arrays and Java direct byte buffers. So you see initially the red line is this buffer, the latency is lower. So obviously we are the buffer API is still doing better. But really even for small messages like 512 and 1 kilobytes, there is a switch point, and we start seeing that while there is still overhead for Java arrays, this extra copy that exists, but because of the way Java virtual machine implement Java arrays compared to direct byte buffers, traversing data stored in arrays is still much faster than direct byte buffers. So this is still an open question right now. We don't have a solution for this right now, but this is something that we are exploring. And this is a broadcast comparison for, let's say, 8 processes. And here you can see we are doing 1.51 times better on average than OpenMPI using the buffer API. And this difference, let me make it clear, it's not only because of the Java interface, but this also exists because of the algorithms implemented in the MVAPICH2 library, and so on and so forth. So I think I've actually taken much more time than allotted time. And so with this, I conclude, I just presented some of the early experiences of implementing Java bindings for MVAPICH2. And we will continue to work on these Java bindings, and we hope to release this to the community in the near future. Thank you.
Yeah, thanks Amir. Are there any questions for Amir? Please feel free to post your questions the QA box or on the Slack. So if not, let's go to the next set of short presentations. Let me introduce people. So these presentations will be done. The first presenter will be Navaras. So he's a PhD student. Again, working on the high performance deep learning project. He just joined his PhD program. His research includes distributed deep learning, HPC, and AI. So he will be talking about, We'll be talking about MVAPICH2 meets Python, enhancing OMB with Python benchmark. Then the second presentation will be done by Kaushik Kandadi Suresh. He is a 4th-year PhD student focusing on the MVAPICH project, but inside that more aspect to the architecture and parallel programming and data types. So he will be talking about simulating large-scale systems with MVAPICH2 and Sandia SST. I indicated about that in my yesterday's talk also. And the final presentation will be made by Arpan. He presented a little earlier. He will focus on accelerating DNN training on the Bluefield. So with this, let's get started. Nauras, would you like to share your slides and get started?
Yes, thank you, Dr. Panda. Let me share my slides. Okay, can you see my screen now?
The window, yeah, now the slides are coming, but yes, it is coming. You can make the presentation. That's correct. Okay.
So yeah, hello everyone. I'll try to keep this brief. Today I will be talking about the MVAPICH, a package that we've been working on to add Python support to the OSU micro benchmarks. This package should be available with the next OMB release. So in this presentation, I will briefly touch on OMB, why we chose Python to add OMP support to, and how MPI is used with Python. And finally, I'll introduce the new OMB PY package and some initial results. So OSU micro benchmarks, or OMB, is widely used to measure the performance of MPI operations on different HPC systems. It offers a variety of benchmarks to evaluate different MPI communication metrics, including but not limited to point-to-point and collective tests. It also provides the users with a wide range of options to run more customizable tests. It supports different platforms like ROCm and CUDA to run on ARM and NVIDIA GPUs. So this package is mainly written in C. So why did we decide to add Python support to OMB? In the past decades, Python has been gaining a lot of popularity. It currently stands as the second most popular programming language according to the TIOBE index. There's a great community and support around the language, especially when it comes to machine learning, big data, and cloud computing. And today, when we talk about the deep learning frameworks in particular, the first thing that comes to mind is Python deep learning frameworks like PyTorch and TensorFlow. So with these kinds of applications, there's a huge potential to use MPI in Python to accelerate its performance. So furthermore, Python is very flexible compared to other lower level programming languages. So for instance, Python aids in designing DL applications much more quickly compared to other languages like C++. Now, how can we use MPI with Python? So basically, to enable MPI functionalities on Python, we need a wrapper to provide bindings with MPI. The MPI for Python package is the most widely used Python package for this purpose. There's also a number of other packages that may serve this similar purpose, like Church Distributed. For OMP-PY, we mainly use MPI for Python as it offers many useful features. It supports multiple Python objects as memory buffers, like built-in Python arrays and NumPy arrays. It also has an important feature called pickle, which can serialize any Python object, let's say a dictionary. So it converts it into a string of bytes and communicates it, then unpickles it on the other side when it's received. Also, recently, MPI for Python started supporting GPU-aware MPI. So to go back to the bigger picture here, this is the hierarchy where OMB-PY comes in handy. We have MPI implementation like MVAPICH 2 that's responsible for the communication. Next, we have MPI for Python, which provides the necessary bindings to enable MPI functionalities on Python. And finally, on the higher level, we have the OMB-PY package to measure the communication performance. So what does OMB-PY offer? It follows a similar design to the original OMB, but it brings it into Python. With the first release, we plan to have support for most point-to-point and blocking collectives. The package mimics the behavior of real Python applications to report accurate evaluation numbers. It also has support for CPU and GPU. For GPU, it uses CUDA-aware memory buffers like CuPy, Numba, and PyCUDA. And like OMB, we have a lot of user flags to run customizable tests. So this is just a sample output for OMB PY compared to OMB. And we can notice that like the similarities in the CLI options. And here we have some initial CPU internode results. This is the OSU latency benchmark. X-axis is message size and Y-axis is the latency numbers. And we are comparing the performance of the original OMB in C to OMB PY. We can notice that there is a small overhead, about 0.5 microseconds, due to the overhead added by the Python binding layer. And it's only noticeable with smaller message sizes up to like 16 kilobytes. And here we have initial GPU internode OSU latency numbers, comparing the different GPU-aware memory buffers like CuPy, Numba, and PyCUDA. And we use the original OMB in C as the baseline. We can see that different memory buffers have different overheads. So it's around like 3 microseconds for CuPy and PyCUDA and 5 microseconds for Numba. Similar to the CPU results, overhead is more noticeable in the smaller message sizes. So to provide a conclusion for this short talk, we've established that MPI support for Python is crucially needed to accelerate a variety of Python applications. We use MPI for Python to provide MPI bindings for the OMPPY package. And this OMPPY new package, it will provide the necessary benchmarks to measure the performance of different MPI operations. Thank you very much for listening. Let me know if you have any questions.
Yeah, thanks, Nauras. Are there any questions for Nauras? Okay. If not, let's, Kaushik, you can get started.
Can you see my screen?
Yeah. Yes. Go ahead.
So thanks for the introduction, Dr. Panda. Hi, everyone. So I'm going to be talking about the large-scale simulations that we did with SST and MVAPICH. So I'll first briefly introduce what SST is, and then I'll talk about how can MVAPICH be executed with SST to get some results, and I'll be showing like a few results that we took using the SST simulation. So SST is basically an open source framework that is used for simulating the HPC systems, and it can also be done serially or parallelly. And SST basically lets discrete simulators to share data so that we can run large simulations. So this slide shows you an example of a workstation. So where you have a processor, memory, NIC, and a router simulator, and SST kind of integrates all of them together to form an entire network. So and basically how SST internally works is it's a standalone application. So you get an executable that you run. When you run it, it loads a bunch of dynamic libraries. So these are called element libraries, and you also need to specify a set of parameters in the configuration file. And these elemental libraries have different components that basically, does your simulation. And SST's API is in C++. So this slide basically shows like a simple example of SST macros elemental library. So SST macro elemental library lets you actually simulate extreme scale application by providing different components like routers, switches, network simulations, etc. So in this slide, if you see, this is a simple MPI program, and in the bottom of my screen, you see a configuration file which says that this is a send receive code, and launch it using API run command with -n2 and so on. So when this is compiled with SST, you will get an executable, and when that is executed, it will simulate an MPI program with two processes, because in the configuration file we have mentioned that we want to run it as a two-process job, and it will basically intercept your send and receive calls to simulate the data exchange and give you the predicted latency. So SST macro internally, how it works is, it basically runs something called discrete event simulation. So it has a bunch of components like your memory, your switch, your routers, and everything. Each of these components, they generate events and they send events to other components. So say your processor sends an event that I have to transfer this message to your NIC. NIC then gets that event from the set of events that it gets from processor and applies its modeling and adds some delay to the packet, and then puts it to the either switch's queue. So from then switch again takes that event and it again applies its model, and then so on. That's how time progresses in discrete event simulation, and that's how SST does it. So as you can see in my slide, components are NIC, router, memory, models that you can specify, and node, which is nothing but your CPU. And SST macro basically intercepts the MPI calls to run the simulation. So in this slide, you basically see a bunch of parameters in the topology, in the bunch of things in the parameter file. So this is how you configure a parameter file for any simulation. So in the top part, you see this thing called app, which specifies how you want to run your simulation, like the number of, how you want to launch it, the number of processes and so on. And next comes the memory and the processor. Memory specifies basically the latency and its associated parameters. And the snapper that's written there is the model that SST provides. So SST provides a bunch of models. Each of them have its own accuracy. More the accuracy, then more it takes to run the simulation. And the interesting part here is it also lets you to choose the topology of the network. You can even configure the geometry of the topology and the type as well. You can do torus and dragonfly and whatnot if SST supports it. And again, same thing goes for switch as well. You can configure it with a bunch of parameters in the configure file. So once you have your parameter file ready, these are the steps that you can use to run SST macro with MVAPICH. So SST transport is a part of the SST framework. It basically emulates the transport library like libfabric. So now, in order to run MVAPICH with SST, you first need to install Clang and then build the SST macro. So once you build SST macro, it generates SSTCC. So think of it like a wrapper, like a GCC, compiler. Now, once you do that, you have to build the SST transport. So this is like building your UCX or libfabrics, your transport library using the Clang again and SST macro. Now, once these two are done, you build your MVAPICH with SSTCC. This is like building your MVAPICH with GCC and linking it with any transport, lower level transport library. So in this case, we have built SST transport, which is like the transport library that we want to link it with. So you can build MVAPICH with SSTCC and link it to the SST transport library. Once that is done, you can compile the program, any MPI program that was basically generated by the MPI CC, which was generated in the previous step. So after building this MVAPICH, you can use that MPI CC to compile any MPI program and add all the parameters that we mentioned in the previous slide to it. And it can be run in this manner as shown below. So this app.exe will be the executable after you compile your program, and SST mac comes from the SST macro that you basically installed. So this runs the entire simulation and it reports the output. So now this is one example run that we did with SST and MVAPICH. So here what we are trying to show you is using SST, we can estimate how your algorithm performs, in a large scale network with your choice of topology and your choice of configuration. In this case, we have taken a simple example that we all know. In this case, we are running allgather for small message, which is on my left side, and allgather for a medium to large message on the right side. So we know that recursive doubling, RD, which is actually good for small messages, and ring is better for large messages. And SST kind of gives you similar trends, even though the exact latency may not be accurate, but SST can give you the trends based on the model that you selected in your parameter file. So why this is useful is, say you're writing or you want to prototype your new algorithm or something in MVAPICH, like a new collective algorithm. You can use SST to simulate on large scale systems to see how it behaves. And another example that we would like to show is where you control topology. So here we ran MPI all-to-all using OMB. And for three different topologies, one is torus, the other one is fat tree, and the third one is dragonfly. As you can see, SST lets us configure the topology, and you can study the impact of topology on our collective algorithms using the SST. So to conclude, SST is a framework for simulating HPC systems, and SST macro provides the required components, and it runs discrete event simulation to simulate your HPC programs on multiple nodes. And we have integrated MVAPICH with SST, which means you can analyze the performance of the algorithms or anything in MVAPICH with SST on a large scale simulation. So as a future work, we would also like to study different things like QoS when run on large scales using SST. Thank you.
Yeah, Kaushik, thanks. Are there any questions for Kaushik? Okay, if not, let's thank Kaushik, and let's move to the last short presentations to be presented by Arpan.
Let me share my screen. I hope you can see it.
Yes, yes.
Okay, great. So So hello everyone again. So in this talk, we are going to talk about how to accelerate the DNN training on Bluefield TPUs. So since we already know about the deep neural networks, distributed training, so I'm not going to talk about them. I'm going to talk about the factors that affect the performance of distributed DNN training. So high performance interconnect plays an important and vital role in achieving good scalability on thousands of GPUs or CPUs. So what makes an interconnect high performance? Low latency and high bandwidth are no-brainers, but there's one more factor that is equally important, which is low CPU overhead. If your network is taking 40% of your CPU, then application developers will not be happy. In particular, the distributed DNN training workloads will not give very good performance, and researchers will not be happy with the high CPU overhead. So that is why we need the high performance interconnect to have a low CPU overhead. Bluefield takes a step forward and introduces the data processing cores into the adapters. So it has a system on chip containing the 64-bit V8 A72 processors, so which can be used for the variety of tasks. Like you can offload the MPI communication to the DPUs, its processing and other things. However, in this paper, we are going to focus more on the deep learning, like what phases of deep learning we can offload to DPUs to improve the performance. So since state-of-the-art DPUs bring more compute power to the network, and we all know that deep learning training needs all the available compute power it can get. So it also needs the compute power from the Bluefield DPU. So that is why we need to optimize the CPU-based DNN training for the Bluefield DPUs. So now, how can a DPU can be exploited for the deep neural network training? So there are several phases in deep neural network training, like fetching the training data, data augmentation, in which we apply the user supplied transformation functions to the input data in order to achieve greater generalization accuracy. Then we have forward and backward pass, which are used in the training, and then we do the weight update and model validation. So the different phases can be uploaded to the DPUs to accelerate the training, but we need to keep one thing in the mind. That is, if we are offloading a phase, it should not be a sequential. So if we are uploading a sequential phase to the DPUs, then we are not doing anything in the parallel. So that is why we need to find those phases which can be offloaded to the DPUs, and we can continue the training on the CPU while we are doing those phases on the DPUs. So the one and the very naive way to accelerate the training is to create another replica for data parallelism. Like we all know that a model replica in data parallelism works independently from the other replica, and we only do one synchronization, that is the reduce operation. So since we know that DPUs are not as powerful as CPUs in terms of cores and the frequency, so that is why we can give less number of samples to DPUs, and we can give more samples to CPUs. The idea is that the overall time for the forward and backward pass should match, so that we can get the speed up. So we use this approach, and here we show that the maximum speed up possible with this approach is 1.04x. And we report, and when we actually ran the experiment, we were getting around 1.03x speed up by offloading the training to the DPUs. So why offload naive does not give significant speed up? The reason is that forward and backward pass are compute intensive, and DPUs are not suitable for these compute intensive tasks. So that is why we need to explore other phases that can be offloaded to the DPUs. So therefore, we propose advanced offloading designs. These designs were proposed in the recent paper, which is published in the Hot Eye a a few weeks back. So you can offload the data augmentation to the CPUs. Like you can fetch the training data from the memory and then apply the data augmentation functions. So that is why we create two types of processes: training processes on CPUs and data augmentation processes on TPUs. So we do the asynchronous communication. So that is why we create two buffers. One buffer will be used for the training, while we will send the next training batch to the second buffer. So each training process has one data augmentation process on GPU in this design. Now the next design is offloading the model validation part to TPUs. So model validation is a less compute intensive task, as we only do the forward pass in this. So that is why we create two types of processes: training processes on CPUs and testing process on DPUs. So after every epoch, we validate the model, and so we can easily parallelize it with the next epoch. So we validate the model on the validation data set. So that is why this data set is equally divided among the testing processes, which are on the DPUs. Now the third design is the hybrid. It combines both the data augmentation and model validation designs. So that is why we are creating three types of processes: training process, data augmentation process, and the testing process. This design is beneficial when data augmentation part on DPUs is not taking as much time as the training time on the CPUs. So we will have some time left on the DPU, so we can use that time to do that model validation. So this is the main idea behind the offload hybrid design. And we use asynchronous communication for the data augmentation and synchronous communication for the model validation part. So now let's see what kind of performance improvement we can get. So let's talk about the ResNet 20 model on the Cypher10 dataset. Since this is a small model, so that is why the data augmentation, the time on the data augmentation on DPUs is roughly equal to the time to train the model on the CPUs. So that is why offload data augmentation is giving the best performance, up to 13.8%. And we show that our designs are scalable also. So we gave the consistent performance over multiple nodes also. Now the next one is the ResNet 56 on the SVHN dataset. So since ResNet 56 is a larger and deeper model compared to ResNet 20, and SVHN is like a Cypher10 dataset only. So that is why the data augmentation time on the DPUs is smaller than the training time on the CPUs. So in the meantime, we can do the model validation. So that is why hybrid design is giving the best performance in this case. And here is the speed up numbers for the multi-node experiments. So now the next one is training the ShuffleNet on Tiny ImageNet dataset. So now we have larger images. Like in Cypher and SVHN, we have 32 by 32 pixel images. However, in the ImageNet, we have like 256 or 128 pixel images. So now the data augmentation time is also increased, and it is roughly equal to the time required to do the training on the CPUs. So that is why offloading just data augmentation will give you the maximum benefit. So we are getting around 12.5% improvement with our design. And as you can see that we are able to get same performance, same percentage of improvement on multiple nodes also. So to conclude this talk, in this talk, we proposed and talked about several offloading designs that can be used to offload the training to DPUs, and we report up to 15% improvement with our proposed design. We have implemented these designs in the Torch, in the PyTorch, we used models from the Torch region. We are using the Horovod and NPI for the data parallelism. So in future, we would like to use the DPUs to accelerate DNN training on GPUs, and we would like to evaluate our designs on transformer models and the strong scaling. So thank you. With this, I conclude my talk. Thank you.
Thanks, Arpan. Are there any questions for Arpan? So with this, I think we'll bring it to the conclusion. The event we had allocated some short time for any kind of feedback people would like to give. Any of the like open mic session. I know people have been continuously providing suggestions, recommendations, but if anybody in the attendees would like to talk, we can unmute you and we can have a short discussion.
Please raise the hand and we can unmute you.
Yeah, that also we can do. Any question, feedback? Is Adam still there? Typically, he asks a lot of questions in this session.
I don't think he's here.
Okay. So if not, I know we are running a little bit. Pardon me?
No, sorry, Adam dropped off.
Oh, I see. Okay. Okay. So let's again. I mean, we are open. Anybody can send us note, but I'd just like to finally conclude. Thanks for attending the 3 days events. It has been very intense. We had a lot of presentations, a lot of things. We had from 20 organizations. You heard from 36 speakers. As of today morning, we had like 239 registered attendees from 154 organizations from 24 countries. So they attended at all different times for different sessions. So we are collecting all the presentation slides. I think some of them have already been linked. Matt will be following up with several of you, the speakers, and Matt or Ben, and we'll be linking those. And also the recording of all the presentations are available. We'll be trying to link them very soon to the website. So before we finally conclude, I'd like to again thank all our sponsors. Their help has been significant here. AWS, Oracle, Rockport, NVIDIA, Excel Solutions, Paratools, Ohio Supercomputer Center, and Ohio State University. So I'd like to thank finally all the keynote speakers, all of the invited speakers, and of course all the attendees. Many of you have been been steadily attending all the sessions on 3 days. So thanks a lot for your time. I would also like to thank the moderators during the virtual sessions. And Matt, he's our webmaster. He has been continuously updating the page for the last 1 month or so. And of course, all the MVAPICH team members and the lab students and staffs and volunteers. And the final thanks go to Hari and Amir. They have been organizing a lot of things in the behind the scene to make this event happen. So with this, I'll formally conclude. I hope next year we'll have an in-person meeting. That will be the 10th year of the conference. So if situation is will be okay for everybody to travel, we'll have a big Mark 22. Thank you.
Thank you all. Have a good evening, good night, good day. Bye.
Bye.